Afternoon, anybody? Yes, 27 of you. So we will start with static equilibrium of bodies, and I hope you have learned in great depth static equilibrium of bodies in your engineering mechanics course. Here we are not going to go into details of static equilibrium of bodies. We are going to deal with only to recap whatever you have learned in the last engineering mechanics course, and probably later part of the course we will will develop from static equilibrium of bodies how the differential stress equilibrium comes. At this probably we will develop later part of this course. Okay, so let's go ahead and discuss about static equilibrium. So the static equilibrium, that what static is very important here, which means you're looking at the equilibrium of the body when the body is not in motion. That means its motion is zero. It can be in constant velocity, but its acceleration is zero. So when we write F equal to Newton's second law, F equal to m into acceleration, right? We are telling that acceleration when the body is in static, that means acceleration is zero, and therefore F summation of F all forces along all directions should be equal to zero. Remember that when I say A, then that should be a bar there to making sure the acceleration is along a particular direction given the forces along all directions, right? So unbalanced force, so the acceleration will be along the direction of the unbalanced force. Now, when we say static, we mean that the body is not in motion or its velocity is not increasing with time or decreasing with time. So not changing with time. So therefore, m into a bar where a goes to zero. Therefore, we have static equilibrium. Forces along all directions is going to be zero. Similarly, if there is a rotating body, then summation of m should be I alpha, right? Okay, and we say that alpha is equal to zero. There is no rotation, right? Rotational acceleration, and therefore summation of all the moments, mo, let me write, moments should be equal to zero. So that's what is static equilibrium, and we discussed a few bits and pieces of it here and there in the last few classes. As we discussed previously, for a 2D, a body which is in 2 dimensions, we are not looking at the third dimension of the body. That means either the body is its thickness or in the third dimension is very, very small with respect to the other 2 dimensions, right? So either it is something like this. The third dimension is very small compared to the other 2 dimensions. Okay, like a paper, A4 paper you have, that's the thickness is very small, so that's a 2D system. That's not a 3D system. Sometimes we also call a system 2D when we can also not call. We can also analyze a system as 2D when we have a large portion of the structure, right? There is this thickness also, but it's almost same all through, right? It's almost same all through, and therefore any cross section that we take will represent the complete cross section of the body, and therefore you can only analyze this cross section, whatever I've drawn here, and that is a 2D cross section. Okay. Sometimes, for analysis, for the benefit of ease of analysis, we do this kind of approximations, and they are not wrong. They are quite correct. Okay, so even for a 3D object, if your one side is very, very large and very, very long, so this side, if you see, this side is comparatively very large than the other 2 dimensions, right? And therefore, in such cases, if you take only at one cross section, you can assume that cross section to be a 2D cross section. For example, if you have dam, you might have heard of dams, civil engineering dams, and those dams, you can take one cross section and you can assume it to be a 2D. Similarly, if you have long pipes, pipelines, so the length of the pipes will be very large, right? Its cross section will be very, very small, right? So in such cases, if you take only one cross section, you can assume and do a 2D analysis on them. So we will discuss more on this later part of the course. But I'm just giving you a hint that those all can be assumed to be 2D. Now, when you have a 2D object and you're looking at the equilibrium of the 2D object, so we are not looking into something else. We are looking at only equilibrium from whatever we know. We discussed that it has to, the forces that we have has to be collinear. Okay? That we have already discussed. And I think some one of you supposed to come back with some solution of that problem with K, right? I can find you. Okay, anyway, we'll do it later. So for a 2D object, we have three equations because it's 2D, and that's because in a 2D plane, a body can have motion along x direction, motion along y direction, and rotation along xy plane, so about z. So that's we call it theta, right? So rotation about z. So it can have three things. One is the body can move along x, body can move along y, or the body can rotate like this. Okay, so that's what it can do in a 2D plane. It cannot go, along z direction because that's not allowed. We have said it's a 2D. So neither it can rotate about y, because if it rotates about y, then some parts of the body will move along z, right? So that's not allowed. Similarly, if it rotates about x, so the body will start moving along z. Some directions, some values of the coordinates will move along z, right? So that's not allowed. So z point is fixed. Therefore, it cannot rotate about x. So rotation about x, rotation about y, and the motion about z are restricted. So it has only 3 degrees of freedom. One is moving along x, one is moving along y, and rotation about the z point, z axis, right? Yeah. So as I was discussing that the body is not allowed to move along x, neither allowed to move along y, neither allowed to move along theta when it's in static condition, right? So static condition means it cannot move along x. So if it cannot move along x, what do we have to do? We have to enforce that it doesn't move. How do you enforce? We put a force on that direction, right? You stop its movement by, somebody, some of your friend wants to run away. Okay, so what are you going to do? If you want to stop, you want to either hold the hands tightly and not allow her to move, him or her, right? So if you want to do that, you are applying some force to stop it. So to stop a motion, we apply force. And therefore, we need to have some force that will stop the motion in this direction. Similarly, if you have in y direction, there is a motion and you want to stop that motion, you need to restrict its motion along y direction. Similarly, if you have rotation, you need to restrict that rotation by applying some moment, right? Something is rotating, you want to stop to rotate it, you have to apply some moment, right? For example, door. Let's say a door is rotating, you want to stop it, you have to give some moment about the hinge of the door to stop it. So that's how you stop things. That's one. Now, second point is, when does a body move? A body moves on application of some force. That's what Newton says, right? If you want to change the direction of a body, or if you want to accelerate a body, or if you want to change its motion, you need to apply some force to move it. Now, a body was in motion and there was a force that was making that body to move, and you want to stop that body, you have to apply equal force, right, to stop it, minimum. So what happens is, if I put an equal force, total summation of force on the body along x direction should go to 0. Total summation of force of the body along y direction should go to 0. And the moment that we are applying should also be total go to 0, right? So these three are your conditions of equilibrium of a body in 2D. Remember, condition of static equilibrium of a body in 2D. Now, if you have two body force, as we have discussed last time, if you have two body force, the moment actually makes you, so your two body force can be, one is along this direction and is in this direction, right? So there will be some unbalanced force and the body will start rotating. Okay, and to stop that rotation, you have to make sure that the body are along the same line to make sure that the moment created by the body is 0. Okay? Because if they are not along the same line, they will start creating some moment, and that moment has to go to zero. So it has to satisfy this moment equal to zero condition. And if it has to satisfy moment equal to zero condition, then they cannot be on different direction. They has to be along the same line and equal and opposite. Okay, that's for two force members. Now for the three force members, again the same condition we have discussed already, that it has to pass through a single point, right? Otherwise the body will start rotating. If they don't pass, then they will create a small eccentricity, and the body will start rotating about that eccentricity. Okay, so that's also is discussed here. Please go through this. Okay, these are all taken from Hibbeler, I think. Yeah, Hibbeler. Yes, so as I was discussing, that if you have a body which is in XY coordinate system with a theta, and the body, you have to give some constant to the body, otherwise the motion will start moving, right? So you give a constant here. So the forces that are generated at the constant are the forces that I was talking to stop the motion, right? If there is this support is not there, the body will start falling under gravity, right? On general, generally if there is no force, it will under gravity certain force, it will start moving downward. So the support will make sure that it doesn't move around this direction. So therefore there will be a force that will generate here in the opposite direction, that will negate, or that will make balance the force that was acting due to gravity. Similarly, the body can be acted upon by many forces, right? All those forces can be assumed, and the moments can be assumed to be passing through a single point. And you can find an equivalent force and an equivalent moment. And that equivalent force and that equivalent moment has to be counteracted or balanced by the force and reactions, moments that are generated by this hinge support here. Okay. Please note that when I say that a body is in static equilibrium, any part or any particle within the body is in static equilibrium. So there is no part in the body that is not in static equilibrium. Every part of the body, when we say that building is static equilibrium, then every part of the body is in static equilibrium. Okay, so any isolated part of the body, if you take it out and draw a free body diagram, under the action of all the forces, including the free forces that we put there, it should be in equilibrium. All right. So these are the few things you should note while understanding mechanics of static equilibrium. Here is one example that we did for a determinate system. So if you have a determinate system, let's say I take a simply supported beam that is drawn here. Okay, with the two supports, one is a roller and one is a hinge support, right? And there is a P force that is acting at the center of the beam. Okay. Now, if I remove that hinge, if I draw a free body diagram of the body, if I draw a free body diagram of the body, then I have to remove this hinge. And if I remove the hinge, I have to give two forces, right? One along X direction, one along Y direction. And similarly, roller is there. If I remove roller, then I have to give only one force, right? Upward direction. Now, remember that we discussed this in the last class, that the roller will not restrict any motion, any movement along that direction, right? So the body can move along this direction. Since the roller is not going to stop any movement along that direction, roller is not going to provide any force that is horizontal. Okay, the body is free to move here, and therefore roller is not going to provide any force that is horizontal. But yes, the body is not allowed to move downward, neither move outward because of the roller. And since it is not allowed to move up and down, it will give a force that is here. Okay, so it will restrict the motion along the vertical direction, and therefore the roller will give a force there. Now look at the hinge. Similarly, we can discuss about hinge, that hinge doesn't allow movement along X as well as a vertical direction, and therefore it will provide restrictions along both the directions. So it will be giving forces along both the directions. So how many unknown forces we have? 1, 2, and 3. So total number of unknown forces are 3: RAX, RAY, and RBY. Okay. Number of equations we have in a 2D frame, we have 3 equations: Fx equal to 0, summation Fy equal to 0, and summation of moment equal to 0. So I can use all those 3 equations. Summation of Fx equal to 0 gives me, there is only one force, so Rax should be equal to 0, right? Summation of Fy equal to 0, there are 2 forces along Y direction, Ray and RBY, and there is this external force P. Therefore, RAY plus RBY plus minus P should be equal to 0. That brings you that RAY plus RBY is equal to P. Now let us take moment. So we can take moment about this point because that can nullify two forces. If you take moment about this, then it will not nullify two. It will also nullify two forces because RAX will go through that point. So anyway, let us take about A. We will get RB, and you see this is my clockwise direction. So if I consider these are my positive directions, okay, then anti-clockwise is positive. So from here, RBY into length L, the arm of the force, moment arm, RBY into L, and this P is going clockwise, right? This moment is going to be clockwise, and therefore it's going to be P into L by 2 minus equal to 0. Now if you solve it, you will get RBY is P by 2 and RAY is P. That comes from the symmetry, also from the symmetry of the structure. Since there is no horizontal force, vertically they are symmetric, right? And since it's vertically symmetric, both the supports will take half of the loads, right? So that's how you solve a 2D problem using equilibriums. And equilibrium equations are used to find forces. Please note this, I'm telling you time and again, equilibriums are used to solve forces, external forces. Now, if you have again a 2D planar body, but now we are looking into an indeterminate structure. We have discussed about this. This is a prop cantilever with a prop here, a roller support, right? So if you have a roller support and a prop, again you can count the number of unknowns. So since this is fixed, it will have three unknowns. One will be RAX, two will be RAY, and the other one is moment MA, because the fixed point, fixed support does not allow you to rotate also, right? And therefore it's going to provide a moment to stop that rotation. And since there is a support here, it will not allow the body to move like this. Either the body has to move and make a 0 point here, zero formation there, and therefore it will provide an RB force, and that's here RB. So total number of unknowns we have 1, 2, 3, 4, and in a 2D we have equations is 3, right? We don't get fourth equation, we get 3 equations only. But then you cannot solve this because you have 3 equations and 4 unknowns. So it becomes an indeterminate system. So what you use is something called deformation to be equal to 0 at this point, and this is called compatibility equation. Remember this term, do not forget it. We're going to use it time and again when we solve problems, right? So that is called compatibility equation, and you have to remember this. So what is the compatibility equation that we are going to use here? The compatibility equation that we are going to use here is that deformation at B because of the support is 0. Okay, we'll solve this some point of time. So this is we have discussed. Now we have 4 unknowns and 4 equations, and sometimes we call number of compatibility equations necessary to solve the problem is number of unknowns minus known number of equations. Okay, right. 2D bodies we just discussed, and we also discussed. So these are the few things that you have to probably recap. What happens when you have a truss member? How to find the forces at each of the truss member? Please go back and start doing this, because we'll solve one small problem in the next class on a truss problem, and how to get support reactions. Okay, so given this force, can I rub that? Yeah, fantastic. All right, so this truss, as you can see, is there are 1, 2, 3, 4, 5, 6, 7, 8 members are there, right? And there is 1000 lb force that is acting here, and you can see both these points are hinged. So if both are hinged, then number of reaction forces are going to be 1 here. Let us give the positive directions of forces, 2 here, 3 here, and 4 here, right? Or there will be 4 reaction forces. So this, let's say this is FAX, FAY. Oh, okay, that's going to be a problem. FX and FFY. Okay, a little bit problem because F is force, F is a point also, right? But can we solve it? it's an indeterminate, right? My equations of equilibrium are 3 for a 2D problem. Equations of equilibrium equal to 3, right? Number of unknowns, support, reactions equal to 4. So it's a supposed to be an indeterminate structure. But can we solve it? Please answer me. Yes or no, whatever. Can we solve this problem?
Yes, sir.
Yeah, who said that? Jai.
Yes, sir.
Yeah, Jai, can you tell me how do you solve it?
We assume forces is axial in all the.
Can't hear you properly. Can you tell again?
We assume forces to be axial along the members,
Okay, and then
and then we solve the equations, the 3 equations on every body.
every member will solve for 3 equations.
Means we can, but we shouldn't. We should not.
Now, how do you solve for these 4 reaction forces? This you have done it in engineering mechanics.
Yes. First we will take the moment equal to 0 about any point.
Okay.
Then same the x along x equal to 0, along y equal to 0. Forces.
And the 4th one, you have 4 equations. Anyone else? Jai has told 3. Okay. Can you all hear me, right? I hope.
Sir, we know for the point B, the forces should be same, right? So FE and EB should have the same force. There should not be any change. So I guess we can remove that point B and then solve further. It will become determinate, right?
Point B.
E, sir. The middle of
Point E. Why?
Like because FE force on FE will be same as force on EB. Like otherwise, point E won't be in equilibrium.
That's okay. So how does that help to solve?
And then I think it will become determinate, right?
No. You have 4 unknowns on the outside itself. So when you solve a truss problem, you don't only look at the outside equilibrium, you have to look at the internal equilibrium also. Okay. Please note, for a truss to be solved, you need to look into both internal and external number of equations. In this case, if you please note that there are 4 unknowns at externally, right? So this is obviously externally indeterminate structure. Okay, this is obviously an externally indeterminate structure. And what about internally? If you want to see internally, you remember that some of you, I think Kanikeshwar or someone, told that a truss has to a truss has to have a triangle, right? But can you see that thing is missing somewhere? It is missing here. This is not a triangle. Okay. So internally, it's not stable. But if you combine both internal and external, it's a very stable truss and you can solve it. For example, you take this point C. There are 2 unknowns here. Right? The other force is known. You use Fx equal to 0, Fy equal to 0. 2 equations. You can solve these 2 points. So that truss is solved. Now come to that point, the other point here, B point. Come to B point. If you come to B point, this truss is known, BC is known, right? There are 2 more unknown problem points, unknown bars. You use again Fx equal to y, Fy equal to 0, Fy equal to 0. You can solve for these 2. Come to D point. Again, you can solve for these 2. All right. And as you have said already, that if you know this, you know this part, and if you know that, you know this part, right? So this two can be solved from this point E by using fx equal to 0, fy equal to 0. Now come to A. Here are two unknowns, right? At A, there are two unknowns, fax, fay, and you know these two forces. So again, you use fx equal to 0, fy equal to 0, and you can solve for these two. Similarly, you use for f point, you can use and two equations, and you can solve for fx equal to 0. Therefore, for equilibrium, for solutions, for looking at complete determinacy or indeterminacy of trusses, you need to look for an equation called m plus r equal to 2j, where m is the number of members, r is the number of reactions, external reactions, and j is number of joints. If they're equal, then you can solve it. That's how we solved this one, right? Had there been another member here, like this, we would not have solved it, because once you come to point B, there are three unknowns and you cannot solve it. Similarly, once you come to D, there are three unknowns and you cannot solve it. And therefore, by using internal instability, we are solving an external indeterminacy of the stress. The total number remains same, because I have increased one unknown here and I have reduced one member here. So that m plus r equal to 2j satisfies. Clear? Please look, the point of discussing this is, we have learned straightforward way of solving structures, right? Various ways, various different ways we have learned how to solve structures. And that's very good. Some problems will be there when you need to think differently. We can solve this also by looking at m plus r equal to 2j and solve it. But why it is still solvable having four unknowns on the reactions? Because I have reduced one unknown here. That's why it is solvable. Had I put one unknown here, it wouldn't have been solved. Clear? And also, since there is unstable internal structure here, okay, I had to put another reaction force here. It's contrary to each other. It's complementary to each other. Had there been only a roller here, if you pull it, this will fall. This will go up. Since there is a hinge, if you pull this, it will not go up, and therefore the structure is still stable. Okay, assume there is a roller here. What will happen? You pull this, right? This point will try to move downward like this. No, it will not fall directly. It will go like this. This is also a hinge, so rotation is possible. So this rod will try to go up. And since there is no restriction by this member, it will go up. So the truss will go like this. It will be very unstable truss. The stability has been gained because of hinge that we put there. Or else you put a roller here, but you have to put a member here. Or a member here. That will make sure the structure is stable. So the point of telling all these things is, just don't do maths blindly. When you are doing something on mechanics, open your mind towards mechanics. Okay, maths is going to help you. Use it to help you solve the problems. Physical understanding is more deeper understanding than only doing maths. But without maths, you cannot solve it. You have to learn that. You have to do it. That will give you a hint that there is a problem and you have to use your physical intuitions. Okay. So do that. I have given a few more problems here. Try to solve them. The solutions are also here. First, you try to solve them yourself. Then you look at the solutions that are given here. Okay. These are all again engineering mechanics problem, and you have all done them in your previous year of first year. Okay. One more 3D problem is also given, which also you can look into and see how we solve 3D problem. With that, I'll stop. This is enough for recap.